with what the lead coefficient is for the most part. So any function that can be written in the form y equals some number times x to some power. This is the reason right here why it's called a power function, because it's x to some power. If k is not 0, because if k is 0, the whole thing just goes away, doesn't it? And a is not 0, because if a is 0, then it just disappears, x just disappears, doesn't it? Becomes 1. It is a power function. The constant a is the power, and k is the constant of proportion, or the constant of variation. And guys, proportion and variation are kind of the same thing. They both mean fraction, don't they? We say that if f of x varies as the 8th power, that's this power, right? The 8th power of x, or f of x is proportional to the 8th power. That's why we call it the constant of variation or the constant of proportion. We can either say f of x varies as the 8th power, or we can say it is proportional to x to the a power. That's usually the way I say it. It's proportional to that. All right, some of the things that are power functions that you see that you don't realize are power functions. Circumference is a power function because it is r to the first power, isn't it? So it is r to the first, so the power is 1. What would the constant of variation be? Guys, the constant of variation, just so you know, is always going to be the thing in front of the variable. So what's in front of that variable r? 2 pi. So the constant of variation here is 2 pi. You getting the idea? All right, so area of a circle, pi r squared. What is the power of this function? Squared, which means it's 2. So what is the constant of variation here? Yes, whatever's in front of that, which is pi. Force of gravity is k divided by d squared. Now, to figure out what the power is on this, you have to bring that up. D comes up and becomes d to the what power? -2. So what is the power here? -2. And what is the constant of variation? Yeah, K. Boyle's law. Volume equals K over P. So now, the P needs to come up. It's the variable. So how do we rewrite this? K times what? P to the what? Not 2. What is the power on P in the bottom? Yeah. P to the -1. So what's the power? And what's the constant of variation? Okay, so do we all understand how to tell if something is a power function? To bring the lead coefficient up. And in all honesty, we're not going to pay attention to anything else other than that lead coefficient, the one with the highest power. So, you try this. In the formula, d equals distance equals 1/2 gt squared. State the power and the constant of variation. No, what's the power? What is that attached to? Nope, it's just attached to t. Yes. So it's everything else other than the variable, isn't it? Okay, so your constant variation is 1/2 g. Is everybody getting that? Pretty easy to figure out, isn't it? Okay, it says write the statement as a power function. Use k as the constant of variation. The area of an equilateral triangle varies directly as the square of the lengths of its sides. So what are we solving for? How would I write this formula? What are we solving for here? So we do A of what are we looking at? Sides, right? So A of S, do you see where that came from? Varies directly, so K times what? Length S of its side, the square of the length of its sides. So how would I write it? S to what power? Second. Do you see how this works? It said use K as the constant of variation, so we knew it had to be K times something, don't we? And then the rest of it told us what the power would be. So what is the power of this function? 2. What is the constant of variation? K. And what are we solving for? We're looking at the relationship between side length and what? Area. Yes. Between side length and area, okay? So now it says state the power and the constant of variation for this guy. This one's a little trickier. How can I rewrite that so it's a power? How do we go between the root form and power form, exponent form? Somebody said it what? It's a fraction. So this becomes 2 times x to the what? Yes. X is to the first power. This is the root, right? Power over root. Do you remember this from Algebra 2? Coming back to you? So now that we have that, what is the power? 1/4. What is the constant of variation? Good. So power, 1/4. Constant of variation is 2. Now, we know what this guy is going to do. It is a root. What does a root function typically look like? We looked at all of these forms. Do you remember what the square root function looked like? This is an even root function. Didn't it look kind of like this? Started at 0 and curved this way? So this is going to look the same way. It's going to be at 0. What do we get? If we plug a 0 into that, what is the 4th root of 0? 0. And 2 times 0 is what? So we know we have a point right here at 0. Okay? So we're going to plug some values in and see what we can do here. So let's plug in 1. If I plug in 1 for x, what is the 4th root of 1? 1. And 2 times 1 is? Okay, so if I do 1, I should get 2. So 1, 2. Okay. What's another root that would have 4? Let's try 16. I'm going to put 16 out here. What's the 4th root of 16? No, that's the square root of 16. Take the square root again. 2. So the 4th root of 16 is 2. Times 2 is what? So at 16, this guy's going to be at 4, isn't it? So what is this going to look like? Does it look like this? Okay, so now I want you to help me figure out how to analyze this guy. What is this function doing everywhere? Let's start with so there's one way we describe it. It is increasing. Good. So it's increasing. Is this thing continuous or not continuous? Discontinuous? Does it have any holes? So is it continuous? Okay, so another way we describe this is continuous. Guys, this is where we're using all this vocabulary we've learned. Is this thing bounded? Okay, it is bounded. Above, below, or everywhere? Below. Good. So it is bounded below. Okay? So if it's bounded below, does it have an absolute maximum or an absolute minimum? Good. What is the absolute minimum? Good. And now, let's talk about end behavior. The limit of f of x as x approaches infinity is what? That means, remember, what does it do as it goes to the right? Okay, it goes to positive infinity. Now, the limit of f of x, is x going to approach negative infinity? What's the lowest x goes on this thing? So we have to say as x approaches 0. So as x approaches 0 to the left, what is the function approaching? 0. Not negative infinity, it's approaching 0. It just creams to a stop, doesn't it? And it's done. This is how we describe a function, isn't it? We could say it's increasing on the interval. What interval is this thing increasing on? From where to where? Yes. So this thing is increasing from 0 to infinity, isn't it? We're just going to use, remember, if it's increasing, we use parentheses. It's continuous from 0 to infinity also, isn't it? And it is bounded below. What is the domain of this guy? Last thing we're going to do. What is the domain of this? Is it all real numbers? Where does this thing start? 0 and goes to where? So the domain is from 0 to infinity. Now, range. Where does this thing start and go? From where to where? What's the lowest y value? To where? Okay. So it's also range is also from 0 to infinity. This is all the stuff that you need when you analyze something, okay? What is it increasing or decreasing? Where is it increasing or decreasing? Is it continuous? Is it bounded? Does it have any minimums or maximums? What is its end behavior? What's its domain and range? Does it have a y-intercept? Yeah, what's the y-intercept? 0. So we could even include that, couldn't we? Do you see all the information you get just from being able to graph it? Okay. I want you to keep and put a star next to this because when it says analyze the function, this is the stuff we're looking for when we analyze. All right? Are we good? Okay. So cruising on. Monomial functions and their graphs. These are going to be super, super simple because they are one term only. Anything where k is a constant, in other words, anywhere we have one single term like this, no pluses or minuses, it's called a monomial function. So for any one of these that's a monomial function, one of three things happens, guys. For x less than 0. It's going to be an even function, it is going to be an odd function, or it is going to be undefined for less than 0. Excuse me. Boy, is it a mind. It's undefined. That would be like this. For example, that would be y equals negative x to the 1.5. So if a, which in this case is this number right here is a, isn't it? It's not the number in the front, it's the variable. That variable is greater than what? It's greater than 1. Be careful. It is going to be an even function if your a is between 0 and 1. So 0.4 is between 0 and 1, isn't it? So So if it is either a decimal or a fraction that's between 0 and 1, that means it's a positive fraction, doesn't it? Or it is going to be odd if, for example, y equals 2x to the negative 3, if a is less than 0. So we've got three cases here. Is my power negative? So this is a negative power. Is my power greater than 1? Or is my power between 0 and 1? So you just have to look at the power on the highest term, on that term. Where does that power lie? It will tell you what the function's going to look like, won't it? So, let's look at these guys and see if we can figure out what's going on. We need to be able to identify which one of these is which. I've got three functions here. I've got the green one, the red one, and the blue one. Each one is one of those three that I just defined for you, used as my examples. So which one of those is undefined? Which one is odd, which one is even, and which one is undefined? Undefined should be the easiest one because the undefined one is the one that will not touch the x or y axis. So this one is the undefined one. Okay? So that one is undefined. So this is y equals what? Negative x to the what? 1.5. So there's my undefined. Okay? That can't be it. It's a equals 1. Here's my problem with this. She's given us two graphs, and I don't know why. Instead of one. Hang on a second, guys. Let's take that out. You know what? We're going to be smart about this. And we're going to look at these. Get out your graphing calculator. Let's see if we can figure out which one's which. Y equals what? What was the first one we had? Negative x raised to the what, 1.5? And hit graph. What does that guy look like? Oh, it looks like that. So of those two graphs, negative 1.5, is it on this graph?
No, it's
It's on the other one. Is it the green, the red, or the blue?
red.
Ah, so it's the red one. So it does hit 0. Makes sense. Okay, so this one is y equals what? Negative x to the 1.5. Okay, cool. So let's put the other one in. Let's put the next one in. Y equals, clear it out. What do we want? 2x raised to the what? Negative, woo! Negative third power? And hit graph. What is that one? Ooh. Ah. So it gives us down here and up here, doesn't it? So is it in the first graph or the second graph? It's in the first one, isn't it? Which one is it? It's not. It's the green. So y equals 2 to the x to the negative 3. Okay. So, last one. Let's graph it. X raised to the what? 0.4? Ooh. Okay. So which one is it? It's in the positive. It's the first graph, isn't it? Which one? Which color is it in the first graph? The blue one. So y equals what? X to the 0.4? Okay. So, now, graphing a power function. How do we graph a power function, guys? This is going to be easy if we want to sketch it. Here's how a power function works. Typically, how a power function works is if this power is even, we're going to look at it this way. If this power is even, then both ends do the same thing. Ends go the same way. All right? So if the ends both go the same way, you know what would be the easiest to do? There are 4 possibilities, aren't there? So if A is even, or A is odd. K is positive, K is negative. So if K is positive and A is even, the graph will look like this. Both ends going the same direction, both ends going up. So if A is even and K is negative, what are the ends going to look like? They're going to go together, but which way are they going to form? Down, aren't they? So if K is negative, it's going to look like this. If A is odd, like a cubic, but K is positive. If A is odd, then yes, instead of them going together, they're going to go opposite, aren't they? Isn't this what a cubic looks like? So if K is positive, they're going to do this. What happens if K is negative? It's going to flip around and do the other way. So if K is positive, it's going to look like a cubic this way. Otherwise, it's going to look like that, isn't it? Okay. So we're going to take this information and we're going to look at it. And we're going to just sketch it and see what happens. So we have to look at this. So this is what? K is negative, but A is what? Even, right? So which way is this guy going to go? Both ends are going to travel together, right? Because it's even. Power's even, both ends together, but K is negative, so it's going to go down. So when we sketch this, we're going to sketch it looking like this. And that's all I'm asking you for is a sketch. So now, tell me, is this guy an even or an odd function? It's an even function, isn't it? It's around the y-axis. So this is an even function. We know that because its power is even, right? What would happen if A was odd? It would be a what kind of function? Odd. Okay. What is the transformation here? What is this 2 telling me? Come on, guys. You know your transformations. Stretched what? Stretched vertically by a factor of, and what's the negative tell me? Flipped over. So the transformation, the negative 2, is going to tell me it's flipped over and stretched vertically by a factor of 2. And that's what we know from this, just by looking at that number and the power, the coefficient in front of the power. I want you to look at this guy. Which one of these ended up being the one that was not touching the axes? Which one? To the negative power, right? So I want you to go back and look. All right, so you try one.
Hey, Steph.
Yes.
Can we have Pierre and Redmond to the cafeteria, please?
Sure.
Thank you.
Yeah, take all your stuff with you. All right, sketch a graph here. So tell me, what do we know about this number? What do we know about K? K is what? K is positive, and A is what? Odd. So can you sketch the graph of this? What's the graph of this guy going to look like? Yeah. Isn't that what we said the sketch would look like? Okay, so let's talk about this. What is the function? G of x is what? Odd or even? It's odd, isn't it? Okay. What's the end behavior? The limit. As it goes towards, as x goes to positive infinity, what is this thing doing? It's going to positive infinity. As it goes to negative infinity, as x goes to the left, what is the function doing? Negative infinity. Okay, what's the lead coefficient? Guys, what's the leading coefficient here? 3, isn't it? All right, so end behavior patterns. Let's just reinforce this. End behavior patterns. Look what we see. Even positive, odd positive, even negative, odd negative. We've done all this already, haven't we? So as x goes towards infinity, let's do our end behavior. As x goes towards infinity or towards negative infinity, what are both ends of this guy doing? Going up, right, to infinity. So that both of those are going to infinity. All right, what about for a negative constant and it's positive, or it's even? So if it's negative and even, what are both ends doing? Down towards negative infinity. If it's odd and positive, positive, negative, right? But what happens if it's odd and negative? It does what? Swaps, doesn't it? As it goes to the right, it goes down, but as it goes to the left, it goes up, doesn't it? Okay. Look, back here. So let's match our functions just by looking at what we know. Can we match these functions to A, B, 1, 2, 3, and 4? Can we match those to A, B, C, and D? Let's start with power functions. Let's see, what can we do? What do we know? Number 1 is which one? It's the fourth root. So it is a root function, isn't it? It is an even root that's positive. So if it's an even root and positive, guys, can you tell me which two? Let's do this the smart way. If this is even root, right? To the 1/4, and this is positive. If it is even and positive, which two of these can it not be? C or D. These are both down below, aren't they? So it's either got to be A or B, doesn't it? All right. Well, even and positive roots, so we've got one that's an even root and one that's an odd root, don't we? But they're both positive. So 1 and 3 have to probably be one of these two things, don't they? So which goes with which? Which one's the bigger root? Which one has the bigger? 1/4 is, isn't it? It's more severe. So which one of these curves faster than the other one does? See what I'm saying? If we're taking a 4th root versus a 3rd root, it's gonna root faster, isn't it? 1/4 is more of a root than 1/3 is, or 2/3. Okay, so which one of these roots faster, A or B? This one goes a little smoother, doesn't it? It's not rooting as fast. It's going 1, on. Look at this guy. See how fast it gets roots over? So, which one of these goes with 1 and which one of these goes with 3? Yeah. A goes with 1 and B goes with, or this is A and this is, B goes with 3. Do you see why that is? If it's got a bigger root, 1/4 versus say 1/3 or 2/3, 1/4 versus a 4 in the bottom versus a 3 in the bottom, the one that's got the bigger number is the one that's going to curve over faster. Okay? Now, that leaves us with C and D for 2 and 4. They're both negative, so we know they're both in the bottom. One of them is an even root, one of them is an odd root, isn't it? We've got -4 and then we've got to a -4/3, or we got +4/3. All right, so which one of those is the -2? What did we see in the previous page? The one that had the -2. Which one of these would C belong to? 2, right? You see how that works? Okay, so this one is C. So then 4 would be D, wouldn't it? It's got that 3rd power. Have you noticed that that 3rd power, this was to the 3rd power, this was to the 1/3 power. 1/3 power, doesn't this one kind of look like this one, but flipped over? Well, look what there. What does that negative in the front do? Flips it over. So between transformations and some of this, we can kind of tell what things are to match them up. So this one's got to be D. All right. Analyzing a power function. Says state the domain, the range, and the intercepts and the end behavior of this function. So you've got the picture. You have the graph. What is the domain of this graph? Where's the hole? Let's put it that way. Where is this not defined? X cannot be what? X cannot be 0, right? So how do we write the domain if X cannot be 0? It goes from where to where? Gone from left to right. How do we write this in interval notation? Come on, guys. Starting at where? -infinity all the way to where? 0. And then from 0 to, yeah. Now, let's talk about from the bottom up. Where's this thing? What's the lowest place this thing goes to? 0. And then it goes where? Infinity. Okay. So the range is 0 to infinity. Does it look like it hits the axis? If it flattens out like that, it's telling us it never hits the axis, does it? So does this guy have any intercepts? So none. End behavior statement. As X goes to -infinity or +infinity, this thing's doing the same thing at the ends, isn't it? What number is this approaching as it comes down like this? What y value is this approaching as it comes down on the ends? 0. So the end behavior is 0, isn't it? Rates of growth. Almost done here. It says it's important to understand that many functions tend to go to infinity as x goes to infinity. Do you see all those graphs? They're all going to infinity, aren't they? Just some are going faster than the other, aren't they? So how do we tell which ones are going faster and which ones are going slower? It says we will look specifically at 2 power functions and 1 exponential for now. We have 2 to the x. That's the exponential function. You know how I know it's an exponential function versus a power function? Where is the x? 2 to the x is in the exponent, isn't it? If the x is in the exponent, guess what it's called? An exponential. Okay? So this is my exponential. And then the power functions would be x to the second and x to the 1/2, right? So we've got to figure out which is which. It shows us the blue one is the exponential. So what do you see in the interval from 0 to 1? Guys, what that's asking you is what do you see here with each one of those functions? Which one grows the fastest? Which one's the biggest from 0 to 1? The exponential, isn't it? Which one's the biggest? Which one's the highest? The blue one, the red one, or the green one from 0 to 1? The blue one. So what we see here is we see that f of x, the blue one, is bigger than, what's the next one? What's the next highest one? The red one, which is k, isn't it? So this is red, this is blue, and this one's the green. So k of x is the next biggest, and then that leaves us with the smallest one in that area as g of x, doesn't it? However, let's now look from 1 to 2. So from 1 to 2, looking in here, instead, which one of those is still the highest? Which one's still the biggest? There, in that next window. F of x is still the biggest. But now look at the green and the red. What's happened? They have what? Which one's bigger now in that window? Yeah, g of x is now bigger, isn't it? Look what happened. So if we're squaring, the square function started off smaller and then went big fast, didn't it? The square root function started off high and then tables off, doesn't it? The exponential was just always the biggest, wasn't it? So do you see the relationship between a root and a power function? That root function is going to start bigger and then get smaller. And then the power function, the square function, is going to start smaller and then go bigger. How can we determine what happens as x grows larger? What are we comparing here to see which function's bigger? The x value or the y value? The y value. So we can compare y values. Okay? Now we can complete the table, but there's no need to. Let's just talk about this though. Which one of these is going to grow faster? X cubed or x squared? So 2 to the second power is what? 4. What's 2 to the third power? 8. So which one of those is going to grow faster? The cube. So if you have to choose straight up between a power and a power, always pick the bigger power. That one's going to grow faster, isn't it? Okay. Which one of these is going to grow faster? X squared or x cubed or x squared plus e to the x? Which one trumps? This or the exponential? What did we learn up top? Which one was always the biggest? So which one of those is bigger, x cubed or x squared plus e to the x? So if it has an exponential, the exponential is always the biggest, isn't it? All right, which one's bigger, e to the x or pi to the x? Which is bigger, e or pi? Do you know what e is? E is about 2.718, and pi is about what? So which one of those is going to grow the fastest? So which one's bigger? Pi. So if it's two exponentials, we just look to see which number that's being raised is bigger. Make sense? So if we're looking at powers, we look at which power is bigger. If we're looking at exponentials versus powers, the exponential always wins. If we're looking at only exponentials, the one with the biggest number that's being raised wins. So if we're looking at that race, that's what we get. All right. We've got a couple minutes left. Let's wrap this up. The very last thing we need to talk about is this. Here it says, facts about relative rates of growth. Any two polynomials of equal degree grow at the equal rates, don't they? Equal degree, equal rates. If you have m and n, the one that grows slower is the one that's smaller. So the smaller exponent grows slower. And a to the x grows slower than b to the x if a is less than b. In other words, if you have two exponentials, this is like e versus pi, isn't it? So this is, for example, this would be e to the x versus pi to the x. E is smaller than pi, so e to the x is less than pi to the x. Get it? And then logs grow slower than polynomials. So I want you to look at these two right here and consider which one grows faster and which one grows slower. What do you notice about these two? What do you notice about the highest power? Which one has the higher power? They are what? They are the same, aren't they? So it is x squared versus x squared, so they grow at what? Same rate. However, what do we notice about 2 to the x and e to the x? 2 versus 2.718. Which one is smaller? So this is less, isn't it? So f of x versus g of x, which one grows slower? Okay, so f of x grows slower than g of x. Does this make sense to everybody? And we finished.